We're going to continue to talk about hydrolysis and look specifically at salts that will change the pH of a solution. Looking at the chart, we're going to try to identify salts where, when dissolved in solution, one of the ions will continue on and hydrolyze, causing a change in the pH. Remembering to narrow it down by looking for examples such as this. Looking for cases where there are cations incapable of hydrolysis, and keeping in mind that what determines this restriction is if those ions are soluble in solution or not. So again, there's some clarity around solubility tables and sometimes some question as to the solubility of certain ions in that list. Regardless, we're going to look through the table and notice that we can see an example here, 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 and here. So in those four that I've highlighted, let's just take a look at a specific one. Let's look at this one. And recognize that when that dissolves in solution, it will 100% dissociate to form potassium ions and oxalate ions because it is 100% soluble. So if we have 0.5 molar of that salt dissolved in solution, we will have twice as much potassium in that solution because of the stoichiometry in that equation. But we will have 0.5 molar of the oxalate in that solution. I know from my list that the potassium will stay dissolved and will act as a spectator ion, but that the oxalate can continue on and hydrolyze in solution. In order to determine its strength as a base, we need to calculate its Kb value. So using our Ka table, we can calculate the Kb value for the oxalate ion. Making sure I'm using the conjugate acid of the oxalate ion in my calculation, I've determined the Kb value for the oxalate ion. I definitely want to make sure I don't make the mistake of looking for the conjugate values here. This would be the incorrect values to use, so I don't want to use that. That's a common mistake. I've set up my ice grid, reflecting the fact that my initial amount of oxalate is the 0.5 molar of oxalate that was 100% dissociated from the salt in solution. I'm showing my conjugate acid-base pairs here to be thorough, but of course we know that when you are showing a basic hydrolysis, you need to show that addition of water, otherwise you won't be able to account for the sudden presence of H on the right side in that conjugate acid. And now I will solve for X. Solving my ice grid using the Kb value, I recognize that the subtracting X term will be negligible, meaning that my percent ionization is expected to be quite low, and therefore I can solve this without worrying about the subtracting X, and it will not appreciably change my result. I solve for X, which represents the concentration of OH minus at equilibrium. I get that answer and take the negative log, and that allows me to determine the pOH of solution, and then I subtract that number from 14 and determine to two significant figures that this will be a basic solution, as expected, because my original equation identified the oxalate ion acting as a base to turn into its conjugate acid. Similarly, I want to look at the chart and see if there's some examples of salts in here where the anion is incapable of hydrolysis, but the cation is. So I'm looking for examples such as this one here, and this one here. I'm going to take a look specifically at this one, as it's a bit misleading and sometimes people overlook examples like this. You can double check your solubility chart to ensure that you believe that this will be 100% dissociated, but we will see that we will create 0.5 molar of iron in solution and triple the amount of chloride in solution, but only the chloride ion is incapable of hydrolysis because it is the conjugate of a very strong acid. So we will continue on with this question and explore how this iron ion will act in solution. So I'm looking at the iron ion and trying to figure out how it can be called an acid. It isn't in my list of alkali or alkaline earth elements that we would suggest that are not capable of hydrolysis, and I actually find it right here. So the hexaaquo-iron ion, or the iron 3 ion that is hydrophilic, actually can donate protons when in aqueous solution to turn into this crazy conjugate here, and its strength as an acid is pretty appreciable. So we'll set up our ice grid with that equation and we'll solve for x. Now looking at those values, I would assume that the x will change my result because 0.5 versus 6 times 10 to the minus 3 is not an appreciable difference. It's not a magnitude of 1,000 times different. So I'm going to leave that minus x in there and solve the equation. So I've solved my ice grid for x. The x represents the concentration of the H plus at equilibrium, and I took the negative log of that answer to get a pH of 1.29 to 2 significant figures. Interestingly, if I had gone ahead and assumed that the minus x was negligible, my pH would have been a little bit different, and so in this case I believe it was valid to leave the minus x in and solve the entire quadratic equation to get an accurate answer to the second decimal place.